In this lecture, which is the second lecture about Unit 10, oscillatory or periodic motion, we're going to look at a special type of periodic motion called simple harmonic motion. So simple harmonic motion, as your textbook tells us, is a special type of periodic motion, and it's characterized by this. Whenever the force that acts on a particle is linearly proportional to the displacement of that particle from some equilibrium, and it's in the opposite direction, the particle is moving in a simple harmonic fashion. Symbolically, we can express that as shown here by the force acting on a particle is equal to negative, because of the opposite direction part, times k, which is some constant. X is the displacement from that equilibrium position. If that is satisfied, we have simple harmonic motion, and there should be something about this that rings a bell. F equals negative kx is Hooke's law. We already introduced this when we talked about energy. So that immediately tells us that there is one particular type of motion that is simple harmonic. Masses on ideal springs exhibit simple harmonic motion. They oscillate back and forth in a simple harmonic fashion. And just a reminder what an ideal spring means, that is a spring that obeys Hooke's law, so that displacement is directly proportional to force, restoring force. All right, let's try to apply this to an example. So let's put a mass on a spring, and we'll say it starts at its equilibrium position such that the spring is not exerting any force on the block. We know that Hooke's law tells us that the force exerted by the spring on the block is equal to the spring constant k times the displacement from equilibrium x. And then the negative sign, as we said a moment ago, tells us that the force that the spring will exert on the block is in the opposite direction of the block's displacement. So for instance, if I push the block left, which direction does the spring push on the block? Well, it pushes to the right. Similarly, if I start the block here at equilibrium again and I pull the block to the right, stretching the spring exerts a force to the left. So it's always against the displacement of the block. Let's try to make sense of this. Because there's no friction, if you notice my note down here once again, the only horizontal force acting on the block will be from the spring, and therefore F, the restoring force, is the sum of forces. It's the only force in the horizontal dimension. So the sum of forces would be equal to negative kx. And the sum of forces is an equation that we already have been exposed to. Newton's second law tells us the sum of forces acting on anything in a single dimension is equal to the mass of that object times its linear acceleration in that dimension, or sum of forces equals ma. This becomes very interesting because we can now combine these equations to say negative kx, the restoring force, is equal to ma. What does that allow us to do? Because acceleration is the second derivative of position with respect to time, that's what this notation tells us. You could equivalently use sort of x prime prime, like a lot of us have been doing in calculus, and that's fine. That means the same thing, but this is another way of saying that a is the second derivative of position with respect to time. Because that is the case, we end up with this differential equation. Negative kx, I'm just starting here from the blue and red arrows kind of meet. Negative kx, the left side stayed the same, equals m, but where we used to have an a for acceleration, I'm going to replace that with the differential expression d squared x over dt squared, because that tells me something about the position on both sides of the equation, right? We have position on the left and then the second derivative of position on the right. That's what a differential equation helps us to do. What does that mean? It means that the position of an object that moves under the influence of a spring force only, or in simple harmonic motion, its position is proportional to the negative of its own second derivative. Because, again, the second derivative of position is acceleration. So, as I change x, the second derivative, or acceleration, changes proportionately, but in a negative fashion. This is where we get to do something really fun mathematically. So because of that proportionality, we can say that if you want to model a simple harmonic oscillator using some kind of equation, you need an equation or a function where the function you start with is the negative of its own second derivative, right? So if you take any function and take the derivative of it twice with respect to time, you need some function who you get the exact same thing, but with a negative sign. So can you think of a function that is its own second derivative but negative? That would be sinusoidal functions. So for instance, the sine of x, if you take the derivative, becomes the cosine of x, and you take another derivative, it's the negative sine of x. Same thing worked with cosine, right? So the cosine of x, take the derivative, you have negative sine of x, take the derivative, you get negative cosine of x. In both cases, these two sinusoidal functions allow us to say that the second derivative of something is its own negative. This has all been a long explanation to say one very simple point, and here it is. When we model simple harmonic motion mathematically, we use sinusoidal functions. These sinusoidal functions that model simple harmonic motion take the form, in general, x equals x max sine omega t plus, this is phi. We'll explain what each of these terms means. All right, now we're going to try to make sense of what each one of these terms means. Starting from the beginning, x here just means position. X max, we actually have a term for this. This is the maximum displacement from equilibrium, or amplitude. In fact, page 391 of your textbook tells us that the formula is a sine blah blah blah. The only reason I'm using x max here is because this is the symbol that your AP equation sheet uses, but it's the same thing as amplitude. Sine, again, we're just using this because you need a sinusoidal function to model the motion of a simple harmonic oscillator. But you could just as easily use cosine, because sine and cosine, if you graph them, are the same thing, just shifted. So you choose which one is more appropriate in a given situation based on the initial conditions. So for instance, if you're graphing the position of something and it starts at the origin or at position 0, it would make more sense to use sine, right? Because sine starts at 0. The sine of 0 is 0. Whereas if you start at the amplitude, or at the largest possible value, you would use cosine, because the initial value of cosine, the cosine of 0, is the largest that the cosine value ever is. Cosine of 0 is 1. Omega is the frequency. We'll have to talk about that in a moment, because you've seen the letter omega before. T is time, and there's an important distinction here. It is not the period. It is a lowercase t for a very important reason. So that's just T, not capital T. Finally, we have this phi symbol. This is the Greek letter, and it means something very, very important in simple harmonic motion. It refers to Indiana University, or the last men's college basketball team to go undefeated. Sorry, had to slip that one in there. Not really, though. So what does it actually mean? It's the phase constant, and we'll explain what that means in more detail in a few slides. All right, let's just break this up. Let's do one thing at a time, starting with x max. Again, that just means the amplitude. So the amplitude is the maximum distance from equilibrium. We've already defined all this. I don't want to go into it again. What does it look like on a graph? Well, here you have it. So amplitude on a graph would be the distance from equilibrium, which is the x-axis, the time axis here, and the peak or valley. So you'll notice those are all the same distance, and that's characteristic of simple harmonic motion, because you achieve the same amplitude twice, once in the positive direction and once in the negative. Again, this is all in the first video. Feel free to go back if you haven't seen that yet. So amplitude on a graph just looks like the distance from the x-axis to the peak or valley. Let's try a different term. Okay, omega. So this is a little bit tricky because you've already seen the letter omega before, and we've defined it as angular frequency in this PowerPoint, but in the past, we defined it differently. Previously, we said omega was angular velocity. Are those the same thing, or are they related in some way? Well, for starters, there seems to be a confusing idea here. Angular velocity was only present when an object was either rotating or moving in a circle. So is simple harmonic motion a type of circular motion? I mean, it wouldn't seem to be the case, right? If things just move back and forth, that's not a circle, and yet it kind of is. There's a way in which they are very, very similar, and I want to show you how. So let's look at this object moving with uniform circular motion, meaning that its speed is constant, although its velocity is changing because its direction is changing. It's got this centripetal acceleration. This object is going to move up and then down and then up and then down. And we've always used a tangential and radial axis system. Remember doing this, right? Like one axis was always from the particle to the center of the circle. We called that the radial axis or the centripetal axis, whereas the other axis was always tangent to the circle. We called that the tangential axis. Well, what if we didn't do that? What if we used a traditional XY axis? We'll put one over here, drawn a little bit weirdly, but only because I only care about the y dimension right now. That's why I drew it this way. think about the position of this green particle in only the y dimension. It's clearly going to move up and then down and then up and then down, but not at a constant rate, right? Its vertical position is changing, but at a varying rate, such that when it's at the top, let me kind of mark what I'm talking about here. Where's my cursor? Here it is. When we're at the top here, or when we're at the bottom here, the instantaneous y-axis velocity would be 0, right? This is when the particle, let's look at the bottom for an example. This is when the particle has stopped moving downwards, but has not yet begun moving upwards. Similarly, at the top of the circle, it has completed its motion upwards, but has not yet begun going downwards. So it's got this 0 velocity. And in an interesting way, it works perfectly like a graph. Remember how the graph of a position versus time function, you could take the slope at any moment, and that's the derivative again, and that would just give you the instantaneous velocity. That works here. That works here. So at the top and the bottom, the tangent line, you know what? Let me switch to my pen so I can actually make this more clear. There it is. The tangent line at the top and at the bottom would be 0, and therefore the velocity in the y dimension only would be 0. Well, what about if I go a little bit further to the side? It's a pretty crappy tangent line, but you get the idea. So now we have a non-zero velocity because the slope is non-zero. What about when I go a little further? So what's happened? We're still moving in the same direction, sort of down the side of the circle, but faster. Like that's a steeper slope than the first really squiggly line I drew up here. On the side, we get the fastest possible slope. I mean, really, if this were a graph, this would be an undefined slope, but this would be the steepest possible slope, a vertical line. And then as we go down the back side of the circle, I am not drawing great tangent lines, but you get the idea, I hope. The slope is going to continue to change as we move around the circle, right? Because that's what curves are. They're just changing, constantly changing slopes. In this case, constantly changing circles have a constantly changing slope. Not all curves have constantly changing slopes, but this one does. So anyway, the slope here is going to be shallower and then shallower here. And then by the time we get to the bottom, we said the slope goes to 0, and therefore the y velocity is 0. That is indicative of a simple harmonic oscillator, and I want to show you how it connects. The green dot in the center of this maroon-colored box is going to show us the same vertical position at all times as the green dot on the circle, such that we can refer to these as sort of analogs of each other, where on the left you have real space, the actual vertical change in position, and in the right we call this phase space, meaning it's an equivalent way of understanding how the vertical position changes. So to kind of summarize all we just said on this slide, is simple harmonic motion a type of circular motion? No, but we can use the same principles to understand it better. Okay, let's finish up with this omega idea. We said it was angular frequency, and another way of saying that was angular velocity. So going back to what you knew from way back in the day, what are the units of angular velocity? They were radians per second. But remember that radians aren't like a real unit. We can just kind of get rid of that. So really, it's inverse seconds, or like 1/seconds. Therefore, when we talk about frequency, we give it a special name, which means the same thing as inverse seconds. We call them hertz. And the symbol is capital H, lowercase z, and it means inverse seconds. It's the units of frequency. All right, we're going to try to connect this now to what we already know about omega. So in the past, when I've asked you to calculate omega, or angular velocity, we would use delta theta over delta t. And the reason I'm using the delta notation here rather than the d, the differential notation, is because we're only using uniform circular motion as an analog for this simple harmonic idea. In other words, we don't really care about circular motion where the speed is changing. This is only analogous to circular motion where the direction is changing uniformly. Therefore, delta is the same as d because the average speed and the instantaneous speed will always be the same thing. Okay, enough of that. So omega is delta theta over delta t. Well, what is delta theta? What is the angular displacement if you complete one revolution, one circle? Well, you could say 360 degrees, but we usually use radians, right? So how many radians are in one circle? 2 pi. There are 2 pi radians. And again, I put that in parentheses because radians aren't like a real unit. They're just kind of like a placeholder. What about the time, the delta t in the denominator? How long does it take any object to complete a revolution? I'm not looking for how many seconds here. Obviously, it's different for different objects going in different circles. But in general, what's the word that means the time for one revolution? That's a period. We call that the period of revolution, or capital T. And therefore, omega, going back to this first sub-bullet point up here, omega is 2 pi over t. 2 pi radians over period. So now that we have 2 pi over t, let's try to do some math with that. The period we've already defined previously is the inverse of frequency, or it's 1 over frequency. So since the period is already in the denominator up here in 2 pi over t, that's like 2 pi times f. That's the same thing. So these are just two equivalent ways of expressing omega, 6 of one, half a dozen of the other. Therefore, I can rewrite the equation with 2 pi f in the place of omega. Neither is better, neither is correct. They're both equally valid. It's just two different ways to express the same thing depending on the information you might have readily available. Lastly, we already showed what the amplitude looks like on a graph. What does the omega value, this frequency value, look like on a graph? You can't see it directly, but you can see its inverse, or period. Let me show you what I mean. So period is the distance, you see on the graph here, from one crest to the next crest. And you don't have to measure from top to top. You could equally measure from bottom to bottom, or from this point here to this corresponding point here. Those would all be the same distance. But that's not frequency, that's period. So if I wanted to do frequency, I could just take 1 over the period because of that expression we already introduced.